So I just want to welcome you all to, I think this is our second Geospatial Forum of the semester. I'm Eric Lenny, for those that don't know me, Associate Director here in the Center. And it's my pleasure to introduce Bill Wheaton, our speaker for today. I worked with Bill a little bit, overlapped at RTI when I was there for a few years after doing my PhD. And so Bill is a senior geospatial scientist and a consultant with over 30 years of experience applying GIS technologies and methods in environmental and social science research. Most recently, he has spent the last 25 years, I believe, at RTI International. 15 of those years, he was director of RTI's Geospatial Science and Technology program. Prior to RTI, he was actually a senior instructor at Esri. I think we all know Esri. And now Bill serves in a consulting role for an RTI project. He's done a lot of great work in developing things like the NHD, the National Hydrography Data Set, which I think a lot of us are very familiar with, as well as public health, NIH related work as well. So with that, I will turn it over to Bill to talk about synthetic populations and concepts for geospatial sciences.
Okay, thanks everyone. Thanks for joining us today. Yeah, this presentation here is going to be fairly technical about a particular data set that we produced, a synthetic population data set. Over lunch, met with some students to talk about kind of career stuff and my perspective on GIS as a career, and since I've been involved in it for a long time. And so I don't know, I was thinking if there's another interest in kind of a general, what's it like in a career in GIS, I could do another one on that topic, not technical. So anyway, so Bill Wheaton, my email address is here. It shows gisgeek@nc.rr.com. Doesn't show RTI because I just semi-retired there last month, but I'm working with them closely. Continue to have a good relationship with them. And then the second name here is Jay Rainier, who is the director of the Geospatial Science and Technology program. His email address is jrin@rti.org. We work extremely closely, and we still do, so if you want to contact somebody in RTI with GIS, geospatial questions or interests, you can contact either one of us, really. Okay, so synthetic populations. I'll describe what they are and how we've used them, how we develop them. Let me first mention some acknowledgements about the work. The original work to develop this nationwide data set was funded by NIH, specifically the National Institute of General Medical Sciences. It's one of the institutes at NIH, for the project called MIDAS, Models of Infectious Disease Agent Study, lots of acronyms already. But they were, it was a large grant project that funded the initial development of this data set. We also are indebted to some prior research done back actually in the late 1990s by a group at Los Alamos National Lab that was developing complex transportation modeling software, and some of the work they did on synthetic populations is what we're putting to use here. And then RTI gave me permission, even though I'm not officially on staff there, to use the materials here today, so I appreciate that. So just some overview definitions and background. So microsimulation, in other words, the simulation of society at a very fine level of detail, like individual people, how they react to each other in the environment. These methodologies aim at building large-scale data sets on the attributes of individuals or households, analyzing public policy impacts on these microunits through simulation of economic, demographic, and social processes. So microsimulation can represent a complete system, okay? So it's not just an abstract component of demographics or environment or this or that. It tries to incorporate a lot of the complexity that we see in the world. And so microsimulation is a kind of model of the different kinds of models out there. Microsimulation and ABM are similar in many ways, agent-based modeling. So the question is, if we're creating large-scale data sets at a micro level, again, individual or household level, where do we get that data? Where do we find a database, national database of everybody in this room? You can't. It doesn't really exist. Well, Census will give you counts. Okay, they'll count how many people live in a block or a block group or tract, how many people have a certain income in that area. So it's counts. There's also a data set that Census provides called the Public Use Microdata Sample, which is a 5% sample of individuals and households. And I'll get into how we use that later. But there really isn't any complete 100% list of households and persons, really, with their characteristics, age, gender, race, income, and so on. You might be able to buy a data set of mailing lists, let's say. You know, you get direct mail, right? So that's a data set that has most everybody's address in it in the country because you get mail. What do they know about you? They know your address, they know your name. If you pay for a marketing database, they do have information about your credit card purchases. They can infer things like your age and your race, and you've probably all heard that story about a direct mailer who sent a mail out to a woman to suggest that she should buy some baby products because they thought she was pregnant from an algorithm, and her husband didn't know that she was pregnant. So they can infer a lot of information from purchasing patterns. But those data sets are really noisy. They're for marketing. They're for selling stuff. They're not for social policy or scientific research. So there's some limitations in those too. So anyway, we have to, this quote here I like from 1999, if we do not have a microdatabase of individuals and households, then we have to simulate it. We have to create one from the best data available. So that's really what we're going to be talking about here, is taking existing data sets, several of them, and building a good representation of every household and person with demographics and spatial components. So what do we use them for? Well, we use them for the agents in agent-based models or microsimulations. Because they account for household relationships, so when we build the one we have, you have a household and then you have the people in the household. Okay, so there's two different kinds of records. And the people are associated with the household. So you know which people are in the household. That's extremely important for some kinds of behavioral modeling and things like infectious disease. Flu is really bad this year. Flu within a household is more likely to be transmitted because it's a contact-based transmission. So if we know which people are in a household, then we can associate a higher likelihood of transmission there as opposed to just random, you know, at a workplace or school and things like that. So they provide a realistic list and data set of de-identified households and persons with characteristics, okay? And we can use them, these characters might be straight demographics, like when you fill out your ACS form, you tell them how old you are, how old the people are in your household, race, whether you have gas heat or oil heat, what your mortgage is, how many bedrooms you have in your house, whether you're a vet or not. There's 100 questions that are all associated in the ACS that we can bring into the synthetic population. On top of that, we may want to assign additional characteristics such as disease state, BMI, health behaviors, which we can assign after the fact, and I'll talk about that. Because these synthetic populations, the individual households, are spatial, we can use them for all kinds of geospatial work. And I'll get to a few of these, but it could be risk, exposure, access, mobility, you name it. I consider this nationwide synthetic data set, I call it data infrastructure, because if you have it, and you have it for the country, and it's on the shelf, and it's ready to go, then you can just grab what you need and apply it. So I kind of see it like a census data set, or like the NHD, or like the NLCD, one of those kind of infrastructure layers that can be used in a lot of different ways. At this point, I don't think the government is using it in that way, although we've provided it to EPA and other organizations in the past. And so one of the reasons we generated this nationwide data set is to eliminate the need for individual researchers to recreate the wheel. A lot of people doing microsimulations and agent-based modeling, they have to figure out how to build these things if they want an agent data set. It's time-consuming, it's slow. They do it for area A because that's where their study is or that's where their university is. And University B, well, they don't have it. They got to make their own. It's very, very inefficient. So part of the MIDAS project, part of our role there was to provide data sets that could be useful throughout the whole research network. So it didn't matter where in the country you were. If you wanted to create a model, you just get the agent data set from us, and you don't have to do that yourself, and it's consistent across the whole country. So on a kind of a data structure and content level, it's really very simple. We have a table of households, one record for each household in the U.S. We have a record of, or a table of persons, one record for each person, and there's a database tie between the persons and the households, an identifier. So this particular household here, I'm going to try moving now so the camera follows me. So, sorry if you can't all see over there, but so there's the household says there's 4 persons in it, and the age of the person who filled out the form, the head of household, is 47. Here's the household income. They have 2 cars. And then you have the person. So there's 4 persons in the household. There's 4 records in the persons table. And there's 4 record for each person. There's an age for each person, sex, race, ethnicity, and so on. We do an assignment of assigning people to schools and work as well as something that we added. But the table structure is very simple. The households have location. So the little blue dot is a particular household that I'm showing the record for that here. So every single household has a location, and I'll describe how we get that in a moment as well. So I'm going to quickly flip over to a website. This is the URL for this is popviewer.rti.org. And this is a interface to that nationwide data set. And I'm just going to show this really quickly. Over on the side here, there's a little close and open tab that brings this table of contents back and forth. And so we can look at different ways of looking at the data. So I can show a map background, which is, I can't remember, MapQuest or somebody. There's a black background, there's a white background. And then you can show different variables being mapped. So this is an income map. Yellow is low income, blue is high income. Here's household size, which is the number of occupants. Blue is 1 person, the dark blue. Yellows and reds are more people. Household or race. The red is Caucasian, the aqua is African American, and Asian is a purple color. And then household or age. The dark blue is younger, the yellows and pinks are older. The pink, actually, the magenta is 65 and older. As you scan around through this interface, you come across some interesting things like this blob right here. That's I'm showing age, 65 and older is the head of household. Doesn't mean there aren't younger people in the household, but generally the householder age is 65 and older. So everybody in that block group is 65 and older. What do you think that is? Retirement, golf course?
Where are we looking?
Sure. That's Northern Virginia, okay. So here's Washington, there's Manassas, so it's outside of Manassas. And then one of the things that's interesting, I clicked a button over here, it's called Quad View down in the lower right. So there's single view where you can look at one variable, and there's quad view where you can look at all 4 variables at once. And what this shows, so each of the 4 maps are zoomed to the same place. And by seeing all 4, you really get a interesting look at the demographics here. And it's a little, let me go to the black background here. So they're elderly people. They are mostly 1- and 2-person households, dark and light blue, 1- or 2-person households. Why would that be? Empty nesters, and probably some spouses are deceased if they're all over 65. This is the income level. So we're looking right in here. It's kind of a mixture. There's some lower income, as the yellow, and there's some very high incomes, the blue. A lot of times in these elderly communities, the income is very low because they're on Social Security and things like that. So unless it's a very wealthy neighborhood, you'll see that in elderly communities. And this is the householder race, so it's almost all white folks living there. You can infer things from one map. Like, let's say you look at New York City, you look at Manhattan. Over half of Manhattan is 1- or 2-person households. Okay, over half. But you can't tell from that whether it's young people who are just out of college and aren't married yet, or if it's elderly people who've lost a partner. So without looking at age, household size doesn't tell you that much because it could be either spectrum. So it's really nice to be able to look at these together. And the important thing is that these are done together. So I am not first making a household size distribution and then an age distribution and then a race distribution and then an income distribution. They're all done together. Okay, so that's where the power is. You may have seen data sets. There's several years ago, there was a lot of these that were getting a lot of publicity. It was like a dot of every person in the country, right? And it had a race, let's say, only race. So you couldn't get this richness in it because it wasn't doing the multiple variables. So you can go to this. This is a public website. You can play around. You can go anywhere you want to go. Once you zoom out to a certain level, it'll show you the map, even if you selected the black background. I've spent hours and hours looking at this because I'm just interested. The other thing you'll notice is that a lot of the space is empty. When you look at a census map of tracts or counties, it's all colored in, right? Because they're polygons. The whole polygon is colored in. Is that a realistic representation of population distribution? Not really. This is much more realistic because we're placing them based on a high resolution population density grid, smaller, much smaller than a block group. Most of the land is unoccupied. We'll just go out here to, I don't know, New York, central New York, Pennsylvania maybe. Where's the people? Okay, so it's highly clustered in urban areas. This is Harrisburg here. So it's quite interesting, and if you have the actual dots, then you have the attributes. It's a database. You can do stuff with it. Okay, I'm going to go back to the presentation here. Okay, so why did we make these originally? It was originally for this infectious disease project, and so the infectious disease modelers would develop a model that would say, okay, how is flu transmitted? What's the incubation period? How many people are asymptomatic? How many people have to go to the hospital? What's the transmission rate from one person to another in a household? Transmission rate between two people in school and work? And they developed these what are called SEIR models. How many of you are familiar with them? So, okay, this is public health stuff here. So susceptible, exposed, infected, and recovered, SEIR. So you start out, you might seed the model with maybe half a dozen people, you're sick, okay? Everybody, let's say it's novel influenza, it's a new one, hasn't been around before, almost everybody's susceptible. You have no immunity to it, okay? So almost everybody can catch it. So certain people catch it because there's a transmission probability. And then there's the infected. Well, some times you're exposed, but you don't get it, right? So not every time do you get infected, and sometimes you get infected, you don't actually get sick, which I never knew before, but that's a thing. And then eventually you recover. And so the model will look at everybody and look at your household structure and where you work based on this data, where you go to school, and they're able to simulate a baseline epidemic curve of flu transmission. And then they want to do some what-if games. That's the whole point of modeling, right? So they might say, well, what if we have a vaccine that's effective at a X rate. Well, they can distribute that. How many do we have? Well, we only have enough for 10% of the population. Okay, well, we'll give it to randomly, or we'll give it to healthcare workers, or we'll give it to people based on population densities. They play different games with a given number of vaccine doses and see how that affects the population curve from baseline. So that's what it's all about. And so I just have a quick view of the results of one of these models. This is for influenza in Pennsylvania, and we just converted it into a Google map. So the yellow is low percent infected, and then the oranges and reds are high percent of infected people. And you can see kind of a wave going across Pennsylvania, and you can see the epidemic start very small and then grow and then fade out over time. And that's this particular model. For each day, they'll have a whole data set of where the people are who are sick, who they got sick from, who is recovered, and things like that. And so we can animate that. Okay, so that was the original use. Also, transportation modeling was a big early use. But there's a lot of other things we can do with it. Let's see, go back here. And so one of the points I wanted to make about this model infrastructure, data infrastructure, is that when you have this data set, it makes it really easy to build models because you don't have to worry about the data. And one example of this is something called FRED, the Framework for Reconstructing Epidemic Dynamics, developed by University of Pittsburgh. What they did is they built an interface for one of these SEIR infectious disease models where you just put in the parameters you want. Like if you look at the 1918 flu, it has a very high transmission rate. General seasonal flu has a much lower one. So, but you can put in the number you want for the amount of transmission, and you can pick any county you want to, other parameters, and it'll run on their server and give you the results. So you couldn't do that without all this data just being there, sitting there. So this is what FRED looks like. So you pick a county. This is Allegheny County. R0 is the transmission rate. 2.0 is really high. And then once it runs the model, it'll give you some statistics. It'll give you a little map, and just makes it easy to get to this model. All right, so let's get into how we make it and how we figure out the geographical context. So most of you are aware of the Census Geography, very important and a ton of GIS kinds of analyses. So we start with counties and gray lines are county lines. So this is Durham County right here, downtown Durham, Research Triangle Park. I think the airport is either here or here, I can't remember. Census tracts are, in this case, are the yellow lines. So there's one there, one here, here, here. Block groups are the black lines. I think there's about 160 block groups in Durham. And then you have what are called public use microdata areas. These are the regions for which the Census Bureau supplies this 5% microdata sample. Okay, so they're areas with about 100,000 people in them. And I can get from Census Bureau 5% of the actual responses to the ACS for this area. Okay, so if you filled out the ACS form in the last 5 years and you happen to be in that sample, you're in this data set, in this area, if you live in this part of Durham. So about 100,000 people, I've got 5% actual data from people who filled out the form with no geographic identifier except it's in this red area and with no personal data at all. So what we do is we take that 5% sample and we clone or sample with replacement to get 100% of the people. So we look at the attributes of each census block group. How many people of this income level? How many households of income A, income B, income C, income D? How many people of race A, race B, race C? How many households with size 1, 2, 3? And we select from that 5% sample to populate the block group with the right number of households and the right set of households to match the estimates for the whole block group. So each block group has the count of households, that's the little blue number, and so we make, like in this one here, it says 1,130 households, we make 1,130 dots, and if 100 of those households are supposed to be single person, African American, with an income greater than $50,000 and over the age of 65, we make 100 of them that matches that. So it's, of those 1,130, there's all kinds of combinations of those characteristics. And then the dots, this shows random. This is the first version we did where we just said, okay, we got 1,100 dots in this area, just randomly put them in there. Now we've done much better at this recently, but this conceptually, we're just making the dots and we're putting them out there. Okay, so this process of taking these characteristics, these different characteristics, and selecting to get the right combination of them in a block group is using a statistical process called Raking or IPF. And it's pretty standard. It's been out there a long time in the statistics world. So we take 4 different household variables, and because we only have a 5% sample, we can't take 10 or 20 or 30 variables and get the right set, because there might be combinations of those 30 variables that don't really exist in that 5% sample. So we're limited to 4 or 5, but we can select different ones if we don't like this set. And then it tries to do the best it can to select households that match these characteristics in each block group. So it's, in a way, it's matched at the block group, so each block group is correct for these 4 variables. Other variables come along for the ride. They're not as accurate because they're not matched, but they're there. But within the block group, we take those however many dots we have and we place them so that they match this. We're using something called ICLUS, which is an EPA population data set. Okay. And so how do we do the placement? As I mentioned, this is your standard block group census, a block group map from the Census Bureau. At least I've chopped out the water. If you take the standard census tractor block groups, there's all kinds of areas that are actually water, not land at all. But this is, say, population count by block group. And so this is what we normally look at from census data, which is counts by area. But we actually know that people are not distributed randomly in these areas. This shows the ICLUS data set. The little white blobs or light colored blobs are where, based on satellite imagery and other sources, there's an estimate, a more refined estimate of where people actually live. So we use this second data set to take those dots and place them where this more high-resolution data set says people live. So when we do that, in this area here, this might be forest or agriculture. Nobody lives there. I don't want to put many dots there, if any. The people for this block group, they all live right over here, okay? And so I want to put my dots there. And so that's what we do. So the yellow dots here are the synthetic population dots. So it's a much more realistic distribution, just straight distribution, even if you didn't know anything about the characteristics. If you're doing a risk analysis of, or exposure analysis from some toxic waste site, this is a better estimate than just these block group polygons. Another thing we've done to even improve it a little bit better is to conflate the dots to buildings. And this is something we did for the North Carolina Department of Emergency Management. On the left here is the standard synthetic population. So you can see it's not really exactly where the households are, and we don't even want them to be because we're trying to be non-identifiable, and people get scared if you get a dot on their house. You can see this. You kind of get the grid kind of idea right here. There's one grid cell here, one here. So this grid cell has estimated from EPA to have a higher population than this one here. But it's not too bad. It's not too bad, this representation. But what we did is we took the households here, since we know the size of the household and income, and we also know whether they're a renter or an owner, we built an algorithm to try to assign those intelligently to residential building footprints. That's these blue things here. The state has a footprint building data set for the whole state, and it varies in quality, but they basically have at least a representation of each one, and some data about size and number of floors and things like that. So using the attributes on the dots and the attributes of the buildings, we basically, in a sense, conceptually, we move the dots into a building. We assign every dot to a building. Okay? So over here, in this map, is the result, and the buildings are now color-coded by the number of households in the building. Okay? So one household per building, a bunch of these over here. These are single household buildings. And even some of these look quite large. I zoomed in to make sure not just a big house. And then you've got ones that are multi-household buildings. So you've got larger and larger apartments. These are bigger. They have more floors. There's more people. So we got more and more dots placed into these. And we try to do it so that, you know, if it's a bigger house, people who have a higher income are in those. And, you know, if we put more renters in these than homeowners, we do the best we can. And these over here, these look like big apartment buildings, but you probably can't see it, but these are individual condos. There's actually 6 or 8 polygons here, so each has one household in it. That's why it's light blue. So the emergency management, they want to know really where people are. They would love it if they had the real map, but they're getting better and better with this kind of thing. All right. Did I say 4? Okay. Not too bad. So a lot of people ask about the accuracy. Rightly so, because we are kind of constructing this data set. It comes from real data, but it's not, we're kind of estimating some things. And so this chart just shows how close we are just in terms of counts, and comparing our results to the margin of error you see in the ACS data. And this is complicated, so I'm going to come over this side so I don't always be on that side. So let's just take the left-hand column, householder age, and I've got these bins here, bin 1 through 7. So householder age is broken up into these bins, age 15 to 24, 25 to 34, 35 to 44, and so on. Those are these 7 bins. And so when we do this across the whole country, and we're trying to get the right number of dots with the right count by age, we then can compare what we got to what the ACS says. It's just a count by household size. And so we look at the 15 to 24-year-old householder age, and we look at what we got, we compare it to the ACS for all 209,000 block groups. All of our estimates by block group were within the margin of error. Okay, so the margin of error, I'm not a statistician, I think it means we think the number is 10, but if the margin of error is 5 to 15, you can't say statistically that it's not 6, right, or 5. So anyway, we feel pretty good about that. In the worst case, we're 38 block groups in the whole country. We were either over or run under the margin of error for household income. So pretty good. And again, for modeling, remember we're modeling here. We're not, it's not, it's not reality, but it's close enough to model. Okay, and if we map the accuracy, just looking at places where we had, we overshot or we undershot, these are what these maps show, and it's pretty good. The deep red shows where we got, and I'm not sure which variable this is, let's say it's householder age. We may have created a few extra elderly households than should have been there, but the worst case is 6% higher. And at the other end, where ACS had more than we thought, it's no more than 6% on the low side. This is by block group. This is by census tract. So there's no more deep reds and deep blues. So when you aggregate up with more numbers, you're going to get better estimates. And this is at the county level. Okay, some other uses. So agent-based model we've been covering. There's facility optimization. So if you've got a dot for every household, and by the way, for GIS people, would you rather have dots or would you rather have polygons? Dots. I don't care about your scale. I want dots. But think about the polygon issues you got. You got overlays, you got slivers, you got, you're trying to do aerial apportionment to make some estimate of this. Oh, they're terrible. If you've got the dots, man, it's so easy. It's so fast. You can just do buffers. You can do network analysis. You can assign every dot to a street. You can do stuff on your phone where you can have it do a little buffer on the server. And we did one of these where it took a guy about a day, build a little website. You drive around, and every 30 seconds it updates a series of charts with an estimate of the population within a mile of your location. It's simple, because you just go, you do a buffer, count them up. How could you do that? Polygons. Garbage. Risk assessment, and by the way, on this, this map doesn't mean much, but I'm going to show an animation of this at the end. It's really a way of estimating the best location for mass vaccination sites in LA. If you can only open X number, where should you put them? So that's what that's about. That's facility optimization. Risk assessment, this is a study we did for EPA. We took 40,000 gas stations around the country. We estimated a groundwater plume of contamination. That's what the plume is. And they wanted to estimate cancer risk from this exposure to this plume. And so in one gas station, we don't even know if this plume is right, but they had to estimate it based on kind of elevation, and our hydrogeologists say, well, if the elevation is here, the groundwater flow is likely to be this. If we do it 40,000 times across the whole country, maybe we can make some good inferences. But this is just one of them. And out of the plume modeling, it's a gridded data set. Here's the gas station, the red dot. If you're directly downstream, you're going to have a higher concentration of the contaminant, and the further away you are from that center line, the less contamination. And for every one of these cells out here, you've got either a concentration of the contaminant or a risk value or something like that. If I've got my block group polygon and I overlay it on this, I'm going to calculate risk for people who aren't even exposed because they're upstream. Okay? But if I've got the dots, I overlay them in the grid, I get an exact value on that dot at that grid cell, and I can do these calculations more easily. Again, for this one map, I wouldn't say, okay, I got the risk exactly right for 6-year-olds, but overall, it's a better way of doing it. Out here, there's no household, so I don't calculate any risk because nobody lives there. This household right up here gets 0 risk. It's very close to the contaminant, but there's no exposure because it's upstream. That's important. Okay, and then the other thing that I'm going to talk about is survey extrapolation and data enrichment. We've got demographics, okay? It comes from the census. Do they know about obesity? Nah. Do they know about food security? No. Do they know about how much you spend on food? No. But we can start adding those characteristics to the synthetic population from surveys. All right, so just to summarize really quickly, so they're de-identified. There's no names, there's no addresses. You can give it to anybody. It's all public data. They're XY point features, geospatially speaking. This data set we build is nationwide, on the shelf. It's a very simple data structure. When we release the data, we release it in ASCII files by state and by county. When we did it originally, it was for this modeling community. They weren't GIS users. They didn't know what GIS was. They didn't have ArcGIS, so we just gave them ASCII files. And plus, we know that everybody can read and write ASCII files. So it's quite simple. Schools and work assignments, I can talk about that later if there's some questions about them. And then they're highly amenable to web service applications because they're in a geospatial database. They're dots. Again, you can do this really nifty, fast stuff as web services. All right, so enrichment. So we want to enrich the characteristics of persons or households, and we can do that based on other survey data, so other data sets. Most surveys, survey data collection is really, really expensive, and so most government surveys might only survey, like the one I'm going to talk about here, is the National Health Examination and Nutrition and NHANES. It's called NHANES. They ask a lot of questions about what you eat, how often you shop, what your income is, whether you have enough food to last you the month, how often you shop at fast food or eat at fast food. Big, long survey, health and nutrition. How many people nationwide do you think get this survey and fill it out? 5,000. Okay.
Is that the response rate or what?
That's the response rate. Those are the observations they get. I don't know how many they send out, probably 500,000. So that's a 5,000 observations. That's enough for them to estimate all kinds of things for the general population, because it's a population-weighted survey. There's no geography at all in their data set, because there's only 5,000 people nationwide. You can't even estimate for a state, what the food security, for example. But we can take those observations and we can say, what is the probability that somebody with this income, this race, this age, and this household size has a food security problem? In other words, they don't get enough to eat, they can't afford to eat. If we can estimate the characteristics that correlate with a particular outcome in the survey, and we have the same demographic characteristics in the synthetic population, magic, we can merge them together. So this one here is a map of smoking risk. Red is high, blue is low. This is from the BRFSS, Behavioral Risk something survey. It's a CDC survey, it's a telephone survey. The CDC will only give you maps of smoking by county or maybe census tract, but here we can get a really high resolution map. Here's food insecurity. This is down in Cumberland, North Carolina. This is a map that shows where people are highly food insecure. They don't have enough to eat, they're not eating the right food, they can't afford food. At a much higher resolution than you could get from other sources. And then this even, here's a map of Celiac Disease. The reds are statistically significant cluster hotspots, and the blues are cold spots. There is a sociodemographic component to celiac disease, so not everybody has the same risk. So we can take those risk correlations with demographics and make this kind of map. All right, I'm going to go into more detail on this for obesity. So we did this obesity map. We submitted it to an NIH challenge where they said, okay, we want new stuff on obesity. We're not going to pay you anything. It's not a contract. It's not a grant. Just give us some stuff. So we did that, and we got second place. Time is going by. This is maybe 2015. And we got a $10,000 award from NIH, which went into RTI's hopper. I didn't get it. Oh, well. Didn't expect to. So the idea here is that you get this survey. This is the NHANES survey. They calculate BMI, body mass index. So one of the things they measure is your height and your weight. And with that, you can calculate BMI. So for every person who filled out the NHANES survey, we know their BMI, we know their age, their gender, their income, their race, their educational attainment. And so the statisticians do their stuff and they say, okay, based on these 5,000 records, if we look at people who are age 20 to 29, female, Hispanic, and they have less than a bachelor's degree, this is the shape of their BMI distribution for those people who match those characteristics. So a BMI of 25 is considered overweight, a BMI of 30 is overweight. So people with these characteristics tend to be pretty good. They're on the edge of overweight, generally the mean. There's some really very obese people, and above 40 is called morbidly obese. So that's 40 here. And there are very few people in this 15 to 20, which is a little bit underweight. If we look at another set of people, a little older, they're 30 to 39, male, Asian, non-Hispanic, and they have a bachelor's degree. This is the shape of their distribution of BMI. And the thing is that here's the overweight and obese category. Here's the maximum, kind of the mean value. It's lower, for sure, than this set of people. And the high end, people who are 30 to 32 and a half here, that graph ends right here. There are no people in these very, very high obese areas, okay? So it's distribution. So what we do is we take the synthetic population and we take every one of these curves, there's 96 of them for every different combination, and we say find all the 20 to 29-year-old females with Hispanic origin, less than a bachelor's degree, roll the dice in distribution, and put a BMI on each of those people. So it's not just one value on all the people who fit, it's a value from this distribution. So everybody gets a unique BMI. And the people who are 30 to 39, male, Asian, non-Hispanic, and bachelors, they have a different distribution. Some people have the same BMI in the two different categories, but in general, these people are going to get a lower BMI than these people. So we get a new value, a new variable on the person table, BMI, for everybody in the country, every adult. Did we need to know the location of where these people are in the NHANES? No, we don't even care where they live because the synthetic population is already geospatial and it's already taking into account age, gender, bachelor's degree, Hispanic origin, race, because at a block group level we're already putting people in the block group who match the right distribution there. So based on that merging of the BMI from the small survey onto the synthetic population, we can then do some really nice mapping and analysis of obesity. And so this map here shows the New York City area, and what we did is we took each dot, each person, with their BMI, and we overlaid it into a 250-meter grid. And we calculated the percent within the grid of people who are over than BMI over than 30. So it's the percent of people who are obese, okay, by 250-meter grid. So we have to aggregate up. If you didn't, and these are all dots, it would really be hard to see. So this is a case where we're changing the data structure from a point to a grid-based structure just to do the analysis. So these orange and red areas are a high percent of people who are obese. The blue areas are areas with a lower percent of people obese. In all cases, it's the percent of people who are obese. Because we're using the synthetic population where there's nobody, there's no color, and you can definitely see some patterns here, right? So our mind can see these patterns, low and high, and it's very useful. But we can also do our GIS analyses to find out, for example, which are these statistically significant clusters. So the first one was percent obese. The second one is by significance. This is a GEDIS board GI analysis, and I'm not a spatial stats person, so I might not be speaking about this exactly correctly. But the red area is where there's a 99% probability that is a true cluster and not a random chance cluster. Okay, so we're very sure that these red areas are actually real clusters, and the blue areas are also clusters of lower obesity. And then we can also look at the Z-score, and you get a more kind of continuous measure of obesity. If I'm doing a study of an intervention, community intervention to reduce obesity, okay, I'm a community activist, or even I'm the government and I want to do an intervention and see whether it's working or not. So I want to pick a neighborhood to do the intervention that's high obesity. I want to go high obesity because I'm trying to reduce obesity. Why should I do it in a place where people aren't obese? Pick a high obesity area, and then for the control, pick another one that's high obese. I don't want to pick another area that isn't similar in terms of that characteristic. So this allows us to pick neighborhoods that are like each other in this characteristic, obesity. So it's quite useful for study design as well as just mapping the problem. If you look at CDC or NIH, they are going to only show you a map at a state level or county level of obesity. So this is a much more refined estimate. Okay, I'm going to mention quickly the issue of static versus dynamic population. So we built this synthetic population data set. This one I've been showing is from, I think, the 2009 to 2013 ACS. We're in 2018. It's already changed. And one of the things we may want to do, not only we want to build a new one with the same method with newer data, but we want to take the existing data and project it into the future. So we want to model the distribution of demographic change. And so we built a model called FPOP, which doesn't really stand for anything, but future, F might be future, POP is population. Anyway, this is useful because a lot of processes we're looking at to study, let's say climate change, it doesn't happen in 1 year, right? It happens over decades. And so if I'm doing a study to assess the impact or the adaptability of a population to, let's say, increase in temperature, I need to look at not only the change in temperature over time, but I need to look at that in combination with the demographic changes that are happening already, right? Because the population is getting older, we know that. So if we have more heat waves and we look 50 years into the future, but we use today's population, it won't be an accurate picture because the population will be older then, there'll be more people at risk. So I'll kind of leave it at that, but this model takes a look at every person, every year, it ages them forward, it kills some of them because of mortality. Younger people don't die as often, elderly people do die more often. We have fertility in there, so women of childbearing age, some of them we create new babies, and we age them, and we do some movement of migration. So at each time step, we're generating a new population based on these sociodemographics. Okay, let me finish, and then we got a few minutes for questions. So this is this facility optimization problem. So as part of the emergency response policy in the U.S., every county has to have a set of locations for mass vaccination. They're called pods, points of dispensing. If there's a anthrax or smallpox outbreak and everybody needs to be vaccinated right away, these facilities already exist. They've been selected, and there's a whole mass vaccination infrastructure where vaccines are stockpiled and they get distributed, and if there's a major outbreak, people need to go and get vaccinated. And so in Los Angeles, and pretty much every county, they've already selected where they would have these mass vaccination sites. So they give the vaccines, they have the vaccines there, they get the public health nurses there, people are told to go drive there and get your vaccine. The problem is that in LA County, they've defined 205 of these centers. Most of them are schools, you know, they don't get too crazy with selecting them. Schools are relatively similar to the population distribution in general. But the problem is they don't have enough people to man all of these. They can't open 205. There aren't enough nurses in the public health department. And so they wanted to look at, if they only have enough people to open 30 of them, which 30 will give them the max throughput of people getting through and getting vaccinated. So this, because there's 3 million households, 8 million people in LA County, and you have trying to select, let's say, 30 out of 205, you do the permutations, it would take decades to run this in the computer to get the actual best answer. It's a, what do you call it, computer science people, it's a big num problem. There's some name, NP big or something like that. What's that? NPR, okay. It's just too big. And so what we did here is we used a genetic algorithm, which is one way of solving these problems, where it attempts to select a solution, see how good it is, and then adjust the solution by, you know, swapping out some points with other points. Is that better or worse? And kind of learning as it goes along, and not trying every possible combination because it would take too long. But what you wind up with is a good solution. Maybe not the best, but it's good and it can be done. So we got 8 million dots, right? We got 205 dots, which are the facilities. And in this case, we're going to select 7. We want to know the 7 best of the 205. And for every single solution, we have to calculate the total travel time and total distance from everybody to all 7 of these places, or actually all 205, and pick the best 7. So it's a huge problem. Uses a genetic algorithm, and I'm not going to show it in real time. This is an animation I made afterwards, but it shows each of the solutions. Okay, so you're going to see these red dots. These are the 7 dots. They wanted a solution for open 7 centers. Which 7 should we pick? So this first 7 is probably just random. And the little graph in the corner here shows a metric about the solution's score. In other words, the better, the smaller the overall travel time is, the better the solution. Okay, and so it starts out. You'll see a little white dot that'll move across here, and I've ordered the solution here from worst to best. But in reality, with the genetic algorithm, it might find a really good solution very early, but it's going to go back and try some other things. So if I were doing it in the order that the solution ran, the white dot would jump all over the place. But here I ordered it in terms of the best to worst. All right. I'll probably run this twice. But so it's the red dots are jumping around, selecting different dots, and calculating the total 8 million people solution to each of those sets of dots. And the white dot here is moving from really bad, so the whites and reds are bad, and it's going to move its way down here into the better and better solutions as it goes along. The magenta and even this dark, almost black color are the best solutions. And you'll see as it goes along, as it moves into better and better solutions, that the dots will stop jumping around so much because it's starting to get ones that really seem to have a better solution than other ones. And it's running 5 generations and I think 100 solutions in each generation, so 600 total runs. And as it gets down here into the magenta areas, you can see the dots moving less and less because it's getting better and better solutions. And then once it gets down to the very end, you'll see that the solution doesn't really improve much. It gets into this black area and is still doing a lot of work, but the solution isn't getting much better, even though the dots are moving, which means that when you get down to this level, there's some cases where you can pick this one or that one, and it doesn't make any difference. The solution is just as good in either one of those.
The distance being calculated, is that straight line or network distance?
Network distance. Yeah. We had to fudge a little bit, where we couldn't actually run it with every single dot. So I'll take that back. That still would have been too big. So we associated every dot with a street segment. Okay, so it's done. The one thing that's interesting is, it probably doesn't matter too much in these areas where you selected, but this one up in Palmdale, this is the high desert if you're familiar with LA. There's a pretty big community out there. It's very isolated from the rest of LA because there's one highway that goes up through that pass to get up there. So if you want to really get the best throughput, you have to put one up in Palmdale. So, okay, I'll finish there. And this video is going to close at 4:30. It's going to stop, so I'll just say thank you, everybody, and the video will end. But if you want to ask questions, that's fine.